There are three types of rocks. Sedimentary rocks, rocks that form after the weathering, erosion, deposit and diagenesis of pre-existing rock, exposed to external factors like weather. Igneous rock, rocks that forms from the melting down of a pre-existing rock and its cooling or recrystallization. And finally, today our main topic, metamorphic rock. Metamorphic rock. Those rocks are results from the mineralogical and structural transformation of a pre-existing rock that has undergone a variation in temperature or pressure or both at the same time. However, these rocks forms without any melting or weathering. So, the mineralogical and structural transformation of a pre-existing rock without any melting, it's what we call metamorphism. So today's topic will turn about two topical questions. How can a rock transform into another rock without melting and recrystallization, melting and cooling down? And what is the relationship between this phenomenon and plate tectonic? Broadly speaking, what is the relationship between metamorphic rock and the geological phenomena that accompany the formation of mountain belts that we are studying in this area? So today's video will try to demonstrate and address the first question. How can a rock transform into another rock without melting and recrystallization? For a better understanding, sometimes we need to visualize the process, so let's make a diagram. Simply put, a rock is an assemblage of minerals in a solid state. Many minerals bound together to make a rock. So we have this pre-existing rock in a diagram made by sorts of three minerals. Mineral A, mineral B, and mineral C, like a triangle. So according to this strict definition of what is a rock, being exposed to a variation of pressure and temperature, or both at the same time, will make this pre-existing rock change. How it does change? Namely speaking, one of the minerals will form a new mineral and it disappears. So here we have, instead of mineral B, we have a newer mineral that's formed due to this change of pressure, mineral D. And according to the previous definition of the rock, this means that we have a new rock. So if a rock is an assembly of minerals in a solid state, then any change of a mineral implies the formation of a different rock. So this different rock is a metamorphic rock. Okay? And here is the diagram. We have pre-existing rock with three minerals, mineral A, B, and C. And a new mineral, a new metamorphic rock with mineral D and C and A. Due to variation, change in pressure, temperature, or both, we have a pre-existing rock that we call protolith turned into a metamorphic rock. Bear in mind, according to Moroccan framework, you need to outline also the mineralogical transformation. So this arrow will also be put in the mineral side. And here you have it, metamorphism. You see, metamorphism. This metamorphism is at the origin of formation of metamorphic rock. Simply put, the protoliths could be sedimentary, magmatic, or even metamorphic. But two conditions to name a metamorphic rock. The change of mineral is done in a solid state, meaning the mineral change without melting of the rock, or erosion, or mechanical erosion. So if this occurs, we have a metamorphic rock. Now, explanations are not sufficient. We need to provide proof of existence of this phenomena. We'll try to prove two things. We'll bring evidence of a mineral change and evidence that there is no melting involved through study of documents and data. Bear in mind, this part of the lesson is a practice and training for the upcoming exercise that you might have in national exam. So just we won't try to complicate things. We'll try to make it simple. Let's start. Here we have three different rocks. We have gabbro, blue schist, and eclogite. Okay. The following data table gives the chemical composition of these three rocks. Here you have it. So let's observe. We notice that they have the same percentage of the molecule of the chemicals. It's the same for all three rocks. So this means that all three rocks have the chemical composition. However, if they have the same chemical composition, why there are three rocks? Hence, we need to study the mineral that compose each rock. Here, a thin section observation through a microscope for the three rocks. We notice that gabbro is made by minerals such as plagioclase and clinopyroxene, and blue schist, it has clinopyroxene but also glaucophane and garnet. However, eclogite, it has garnet and jadeite mainly. We notice that for each two rocks they have a common mineral, sort of a logical connection. And we already know that gabbro is not metamorphic rock. So this means that gabbro is the protolith. And it has pyroxene. Which rock that has also pyroxene is blue schist. They have this mineral in common. Therefore, there is a logical link between gabbro and blue schist. However, they have a different mineral. Gabbro has plagioclase, and blue schist has a new mineral that's formed. It's glaucophane, not found in gabbro. Second observation. We notice garnet is present in blue schist, but also in eclogite. Eclogite has no clinopyroxene or plagioclase. However, it has this mineral in common with blue schist. So there is a logical connection between blue schist and eclogite. However, eclogite distinguishes itself by jadeite and blue schist by glaucophane. Therefore, we know first that gabbro is not a metamorphic rock. However, it has a mineral in common with blue schist, and blue schist has a mineral in common with eclogite. Eclogite has no mineral in common whatsoever with gabbro. This means only one thing. Deduction. Gabbro was the protolith, and due to increase of temperature or pressure or both at the same time, we don't know for now, one of the minerals changed, and as a consequence we have glaucophane forming and garnet. So blue schist results from gabbro being metamorphosed. So the protolith is gabbro, it turns into blue schist. At the other side we have blue schist that has some minerals being exposed to increasing pressure, temperature or both at the same time. We don't have proof. New mineral forms which is jadeite. As a consequence, blue schist will turn into eclogite. So eclogite results from blue schist being metamorphosed. Here it's a practice to how to demonstrate the origin and the relation between different rocks and data given in any exercise, how to demonstrate metamorphism. So I don't say that you need to do exactly the same as I did demonstrate now. However, you get the gist of it. Okay, you must proceed in a similar way to this demonstration during exercise, given the tasks that they ask you to do, and exploit, document, and highlight the change in the minerals. They focus on the change in the minerals. So we have this diagram. Gabbro will turn into blue schist and will turn into eclogite. Here is our first bullet point. We made evidence of a mineral change. However, nothing says that blue schist and eclogite didn't melt, are not the result of a melting down. A change of minerals does not give us enough data to prove that there is no fusion and cooling down afterward. And bear in mind that our topical question for this video is how can a rock transform into another rock without melting and recrystallization. So we need other documents and data study to prove that there is no melting down. And this will go through studying the texture of rocks. In the previous lesson, we studied texture of two igneous rocks. We have two major types, grainy and microlithic. Microlithic, we have some chunks of mineral in form of crystal that are surrounded by glass or microlites. Those minerals have a random shape. Grainy, all crystals, all minerals forms in a large sized crystals, however they have random shapes. Grainy is the result of melting down and slow cooling, is specific to plutonic rock. Microlithic is melting then cooling fast, it's specific to some volcanic rock like andesite. What we are going to do now is to compare the texture of the three previous rock and deduce if there is a melting according to this texture. We start with gabbro. Gabbro has a ruggous touch, and we notice at the texture, if you observe texture through a microscope, it's similar to grainy. Random mineral having random shapes and large crystal, and it's grainy. It's grainy also in the touch. This implies that minerals have been melted and recrystallized in a slow manner, making them growing bigger and have random shapes. Gabbro has a texture similar to igneous rocks. Well, that's an evidence because it's a plutonic rock. Okay, so there is a melting down process for making gabbro. Now, blue schist. At the observation with the naked eye, blue schist seems sort of layered. We notice there are some layers. Okay, and at the microscope, polarized microscope, we notice that those layers form like an axis of orientation. The minerals have a shape that is turned towards an axis of orientation. And if we compare, it's neither similar to microlithic or grainy texture. It's a new texture. This texture is specific to some metamorphic rock. Here you have a diagram. We have mineral in the beginning. Then dew schist has that texture not similar to igneous rocks, and due to external force or pressure, those minerals inside the rock will start being squeezed, sort of, due to pressure mainly. And this squeezing make them oriented toward an axis. This is what we call schistosity. You see, pressure made them oriented in a particular way, and every schistose rock is called a schist. So schistosity there is no melting down whatsoever. There is pressure involvement about uh, placing each mineral on a oriented manner. So blue schist is not a result of any cooling or melting down. Okay, and here pressure is highlighted through this axis. It's always perpendicular to the axis of orientation, minding few exceptions. Now what about eclogite? We notice at the first eclogite is spotted. However, it's not grainy. There is a difference between grainy and spotted. We notice also there are some layers of green and white interrupted by those spots of red mineral, that is garnet. We could not say that is grainy. Okay, and if we observe through the polarized microscopes, it's not microlytic. We have crystals that have a geometrical shape. However, the non-initiated or taking a quick glimpse will make us jump into conclusion that is grainy through by saying it has similar shape to the second picture. We could not say this because notice, when in eclogite each mineral has a geometrical shape, sort of geometrical shape in a repeating pattern. Notice it? And for the grainy structure, you notice crystals, although they are the same mineral, they could have random shape and they are larger. But in case of eclogite, we have minerals that has repeating shapes and repeating pattern. Compare it to the grainy, we could deduce it's not the same structure. Okay, this texture is not the same. It's neither glassy or grainy. So eclogite has not a texture that corresponds to igneous rocks. For the specialists, I will not mention the texture because I think it's outside the topic of Moroccan framework for the baccalaureate. And the texture study indicates something very clear. There is no melting and cooling down whatsoever for making blue schist because it has a schistose structure, and also for eclogite, the texture that is not in program. So there is no fusion. Gabbro will turn to blue schist without any melting and cooling down, and blue schist will turn into eclogite without any melting and cooling down. So there is no melting, no crystallization involved. Check. Therefore, this mineral change has been done in a solid state. This means that there is metamorphism involved into their formation. Now we confirm that metamorphism is involved for making those two rocks, and it's linked to change of minerals that makes a rock. We still didn't answer the topical question. We just proven the phenomena. So even if certain minerals have the same chemical composition, they will have different properties. We need to prove it. Case in point, here, calcite and aragonite. Those are two different minerals. However, they are made of the same molecule, yet they have different properties. One is non-colored, the other is yellow brownish. One has a mass volume from 2.6 to 2.8 gram per centimeter square cube, and the other has 2.9, 3.0 gram per centimeter cube. Therefore, same chemical composition with different properties. This implies that those two minerals will not react the same as a variation of any physical parameter such as pressure or temperature. So each mineral has different properties and will therefore not react the same way to variation in temperature or pressure. And also this implies that each mineral has a range of temperature and pressure where it can form and remain stable. Okay, so each mineral could form on a particular range of temperature and pressure. Here it is. Case in point, temperature. We have this temperature range here on this diagram. At the same time we have this pressure range. Okay, if we link the dots, we have what we call the stability domain of a mineral. We call it mineral A. Okay, here is the stability domain. And we know in an ever-changing environment such as underground layers of Earth, there will be variation of temperature and pressure according to geological phenomena related to it. So there will be this variation. If the variation of temperature or pressure or both is significant, the mineral original range of stability will be exceeded. Therefore, we will move to another stability domain of another mineral called mineral B. As a result, a new mineral B will form. We'll have at the beginning mineral A, and now we have mineral B. And we know a rock may contain both mineral or even several. Look, in this diagram we have the green shape. It indicates a rock or a domain of temperature and pressure where a rock could exist. It overlaps mineral A and B. This means these rocks contain both mineral A and B. Okay? And this group of minerals with more or less similar formation condition that go into the formation of a rock that is metamorphic, it's called metamorphic facies. Here we have metamorphic facies 1. Oftentimes the metamorphic facies take the name of the rock that contain most of the mineral overlapping these facies. Case in point, we have blue schist facies. Blue schist facies oftentimes is related to the facies where minerals such as glaucophyne, garnet and pyroxene are stable, and we will find blue schist. Now, if variation of temperature, pressure or both continue, a new mineral will form. Here it is, mineral C. Therefore, if mineral A disappears and mineral C appears, we'll move to a new facies, metamorphic facies 2. So we go from rock 1 to rock 2 without any fusion whatsoever. Here you have it. In the beginning we have a rock 1 in metamorphic facies 1, then we'll move to a rock 2 in metamorphic facies 2, and we have metamorphism. The rock 1 will be like protolith for rock 2. Now let's make a summary. Metamorphism. We have proven how a rock can transform into another rock without melting and recrystallization. So solid state transformation by doing the following. We have proven an evidence of mineral change. We have proven that there is no melting involved by studying the texture. We have identified specific texture for metamorphic rock, just as schistose structure. We have proven through a diagram there is a stability domain of minerals, a range of pressure and temperature where they will stay constant and stable. And we have proven a metamorphic facies, sort of range of many minerals that could coexist and a rock, metamorphic rock, could form. Therefore, so a rock as a definition is an assemblage of minerals Each mineral has its own characteristic, although all the minerals would have the same chemical composition. So, if due to geological phenomena, temperature or pressure shifts, the original mineral become unstable and transform into another mineral. And this transformation will metamorph the original rock called protolith into a new rock called metamorphism without any change of state, without fusion and without cooling down. And here you have it, a simplified definition of metamorphism. So I think it's the end of this video. We have answered the first question. Now we need to highlight the utility of studying metamorphism by answering the following. What is the relationship between metamorphism and plate tectonic? And this will be subject of another video. Hope that my explanation and demonstration were clear. See you on the next video.